think we can start. So the next speaker is Professor Okamoto from Tokyo, and well, how do you pronounce the university?
Gakushuin University.
And the title is Some Thoughts on the Role of the Convection Term in Fluid Mechanical PDEs.
Well, thank you very much. First, I'd like to thank Isaac Newton Institute for invitation and support. I am now enjoying the summer of Cambridge, which is almost autumn in Japan. Now, today I want to say something about abstract theory of evolution equation. I'm sorry, it's not directly connected with the water waves, but it has some connection through the well posedness. Now, before that, I want to give two slides, which is simply advertisement. One advertisement is that my academic grandfather, Hisashi Okamoto, was exactly 100 years old this year. He died many years ago, but he left many legacies in Japan and the United States. So we have some conference. Yeah, another one is in 2023, we have a Congress on Industrial and Applied Mathematics, which will be held in Tokyo in 2023. And Congress mainly consists many mini symposia, and I want many of you will come to Tokyo for mini symposia. Water waves, of course, and any other topics of applied mathematics are welcome. So this is my advertisement. Now, today's goal is this. I want to say some propositions which I found and reported in these papers. And that is very curious propositions, very old propositions. But before that, I want to explain what is the matter. So I will mostly consider the Navier-Stokes equations, okay? Navier-Stokes equation is a bad problem. It's a good problem too, but in some sense it's a bad problem because it's very difficult. So, but it is good because you can write papers. But very difficult part remains almost intact. And so one of my friends in physics said that turbulence is a bad problem. Turbulence is a bad problem because it is too difficult. You can write papers, but understanding the essence of the turbulence is very difficult from the physical point of view. That is his advice. When I was very young, this was advice from an established physicist to young mathematicians. And after that, I didn't consider turbulence seriously. But there are many simple models, like today I'm going to talk about Proudman-Johnson equation. Both are English, Konstantin Lax-Meyer, and generalization, and surface quasi-geostrophic equations, and model equations for water waves too. So those nonlinear models I want to consider today. Well, Navier-Stokes equation is nonlinear and non-local. This is well known. It is best seen in the vorticity form. This is a vorticity equation, and vorticity is obtained by Kerr. And vorticity equation And this one, nu, is a viscosity, kinematic viscosity, and we call this viscosity term. There are two nonlinear terms. This I call convection term. This one I call stretching term, because vorticity is stretched and the vorticity becomes bigger by this term. And this one is convection. Okay? And U and omega is connected by Biot-Savart law, which is represented in this way by the integral. So this is a well-known formulation by vorticity. Now, by the way, when we consider water waves, we have dispersion term. But today, I do not consider dispersion term. Now, when I was young, about 30, I went to many workshops in Japan, and both mathematics and physics. And the people often said this way. I call it folklore. I do not know what is the best English term, but it is something like this. The vorticity is increased by the stretching term, and the convection term does not increase, although the vorticity is rearranged by that. As far as global well-posedness is concerned, the convection term is neutral, because this stretching term, this is omega, this is a kind of non-local omega, therefore this is a kind of omega squared. Therefore this causes the stretching of omega, and this one is convection. So it moves this way, not this way. So this was the I call folklore. So many people said this way, but recently I am thinking that can these loose propositions be phrased mathematically in some way? So this is my question, which I want to explain today. This one is not a mathematical, no. It's rather, well, how should I say? It's not a quantitative. The mathematical proposition must be quantitative. Now, I want to show Proudman-Johnson equation, which appeared in 1962, which is this one. U is unknown. Unknown function of time t and x. X is a space variable, single space variable. And differential equation is this. And nu is a viscosity. There are many, many boundary conditions, but today I restrict myself to the case of the simplest one, that is periodic boundary condition. And of course, we can consider the Dirichlet boundary condition and others, but today I do not consider it. Okay, why this differential equation? It goes back to 1911, when this German guy, Hiemens, considered this kind of picture. In fact, he considered, this is his paper, and his motive is very clear in this page. He wanted to analyze laminar boundary layer. Yes? And he made this assumption, or others. U is some function, and U, this bold U is velocity, two-dimensional velocity of the Navier-Stokes equation. And U is a scalar function. And this satisfies divergence U0 automatically. So divergence-free condition disappears under this ansatz. And then he puts this ansatz into the two-dimensional Navier-Stokes equation. Then only this one remains. This is the fourth order differential equation. And he solved this equation numerically in 1911. And they obtained the picture something like this. Now, Proudman-Johnson considered not only stationary solution, but also he considered time-dependent solution. And that is the equation which they found in their paper in 1962. And this is it. And we consider periodic boundary condition and initial condition. Do you think this is easy enough? Because two-dimensional Navier-Stokes equation, as far as well-posedness is concerned, the problem is settled. It is well-posed in two-dimensional Navier-Stokes equation. But look at this. This velocity field is proportional to y. It's linear in y. So that means it is an unbounded function of x and y. So it cannot be L2. I mean, energy is infinite. If energy is finite, then we can use the theory of existence, local existence, global existence, everything. But this is not. There is no energy inequality, which is the starting point of the existence theory. And we can't use it. So it's not trivial. Now, let's see. This is a Proudman-Johnson equation. And I define omega by this. So minus u, the second derivative of u, is defined as omega. And then this is equivalently written in this way. And this one is a three-dimensional Navier-Stokes equation. But here is stretching term here and the convection term here. Yeah? So both exist.
Can I ask a question?
Yes,
because that's like your folklore statement. Certainly with this equation. No. Leave it where you headed.
This one.
No. Go back to the slide you were at, please. No, not with the omega.
Omega. This one?
Yeah, this one. So if I look at the vorticity equation, if I take nu as 0 and I interpret it in a Lagrangian sense, then 1 over omega material the omega dt is the nonlinear term. If now u of x is positive, then in a Lagrangian sense, omega or log omega goes up, right? So what's wrong with that statement?
No. What I said is that well-posedness, global well-posedness, is not guaranteed by this.
What?
That's the thing which I told. Okay?
This is the case for SQG, right? You say the SQG is the same.
What?
The SQG will have the first two terms, and of course it's not known because global.
Of course, yes, you're right. Yeah.
So the other, they are
Because they don't have a suitable a priori estimate. Yeah. So, but this one is not directly related with that folklore. Folklore is, I come back to that later. Now, thinking of this, I invented this equation, which is different from the Proudman-Johnson because there is a, constant a here. If a is 1, that is the Proudman-Johnson equation. Now, I found that if we consider axisymmetric Navier-Stokes equation in the m-dimensional Euclidean space, then if A is this one, the solution is reduced to this one. Any m. 3 dimension, 4 dimension, 5 dimension, any dimension. If A is -2 and nu is 0, then this is a Hunter-Saxton equation, which is part of the integrable system. And another one, the Burgers equation, which you know very well, I think. The Burgers equation here. I differentiate this Burgers equation twice in x. Then it becomes this, and that one is the case where A is -3. So those equations are included in this generalized Proudman-Johnson equation. Now, I wanted to know the well-posedness. Now, global existence or finite time blow up. This is a problem which I wanted to answer 20 years ago. This one, three-dimensional Navier-Stokes equation, is this. Therefore, from omega to u, it's order -1. Okay, Biot-Savart is order -1. I mean the pseudo-differential equation, integral, so it's -1. But in this case, Proudman-Johnson equation, this is order -2, because if omega is continuous, u is C2, something like that. So this one is more regularized than the three-dimensional Navier-Stokes equation. So there is a possibility that we have a global existence, no singularity. But let's see. I want to show this first. This is a picture of uxx, that is omega, essentially. So omega's max norm, L infinity norm, I computed. And then in a very small time interval, initial time interval, it becomes very big. And then after that, it goes down and eventually goes to 0. So every time I computed numerically, but I'm sorry. Oh, I'm sorry. Well, actually, in 1989, a paper appeared in Journal of Fluid Mechanics. In that paper, the authors predicted finite time blow up for this equation. They presented a numerical example, and it becomes very large. So they conjectured that this equation, Proudman-Johnson equation, do not admit the global solution for some initial data. I didn't know at that time. But around 2000, I was talking about this equation, And I said, I don't know the well-posedness. Then in the audience, there is a Chinese mathematician, young Chinese mathematician, who came to my office perhaps 3 or 4 days later, and he told me that I can prove it. And later it becomes a paper. It appeared in 2000. The paper proposition is something like that. Assume that viscosity is positive. For any initial data in L2, a solution exists uniquely for all t and tends to 0 as t goes to infinity. And boundary condition can be Dirichlet, Neumann. But so I was very happy because my intuition and my numerical computation was right in the sense where posedness is proved mathematically. But there are other questions like Grandi and McLaughlin, who computed the solution in this non-homogeneous boundary condition. And then they said that there is a blow-up. And our proof does not work in this special case. And that was very strange to me, because we are considering the same equation, same initial data. The only difference is the boundary condition, in which only constant appears, non-zero constant appears. And then I don't know why. Because blow-up for global existence is usually determined by the nonlinear term, differential equation, not boundary condition. But in this case, they predicted the nonlinear, blow-up.
Is this numerical?
Numerical, yeah. And I computed numerically too. And I think they are right. But in that case, I can't prove. So I'm talking this kind of stuff again and again. I'm very sorry if you have heard this before, but I'm expecting something like my Chinese friend, Xinfu Chen, appears again to me. Here's the proof. Proof is that we differentiate this equation in x. Then we have this one, and there's something miraculous here. There is no third-order derivative in this equation. It disappears, cancel out here and here. Okay? So if we differentiate x in the x, then ux's x appears. But it cancels out because uxx appears here. So disappears. That is, there is no stretching term in this form. Then we will use the maximum principle, and we use this one. This one is, of course, 0, always, because we consider periodic boundary condition. Now, this is not all of the proof, but the essential part is here. Seemingly, there is no a priori estimate in this form. We couldn't find any usable a priori estimate. But once we differentiate this equation, we have a maximum principle. And this is the starting point of the estimate. Now, there's a proof. A mathematician says, if there is a proof, you need nothing more. That's enough. But physicists do not say that way. They say, oh, proof is proof, but we need some intuitive explanation. So I want to give you in this way. Now, suppose there is the evolution equation. At time t, solution looks like this one, this black one. Okay? Then, by the evolution, if convection is not here and only stretching term exists, then it becomes larger and larger by stretching term, the big, big, big. This one is not big. And so without convection, the higher becomes higher still. So intuitively, we can say this way. But if there's convection, then there's a combination, convection and stretching. Then from this one, this black one, it is shifted to the green one by the convection term. So intuitively, I'm not saying a mathematically rigorous proposition, but here is it. And then from here, we act the stretching term. And as a consequence, this is not so big. Therefore, the question is, if there is no convection, it goes this way. If there is convection, then it goes down first and then magnified, but it's not so magnified as the red one. So this is so convection term is a kind of a government. Without government, capitalism in the world of capitalism, rich becomes rich, and then government acts, it distributes money, then it's not so big. So this kind of stuff is happening in that Proudman-Johnson equation, I believe. And then I considered something different. That is surgery on PDE. Do you know appendix? Appendix is a small organ here. It's not, usually it's considered to be unnecessary. It's not totally unnecessary, but if there is something bad here, then the doctor remove the appendix. And this kind of surgery can happen any person. So if appendix is removed, we still live. Therefore, appendix is unnecessary as far as life or death is concerned. And my question is, the convection term, is that appendix in the evolution equation, particularly in the fluid mechanical equation? So this, now, before I go into the special equation, I want to talk about the simplest example. That is the Burger's equation. The Burger's equation here, we know that it has no singularity. It's smooth. Solution is smooth, always. I differentiate. In X, then I have this one. Now I define W by UF. Then this is there. Now, this is a convection term. This is a stretching term. Now, convection term is appendix. So I remove it. Remove, I have this one, nonlinear heat equation. And it blows up. This does not blow up. Therefore, this removal was something serious. In conclusion, this convection term was not an appendix. The similar thing happens here. This one is a Proudman-Johnson equation. This Proudman-Johnson equation, I remove this one, convection term, dropped. Then I have this one. Then I can integrate this equation to have this equation. And I define capital U by this. Then I have this one. I'm sorry, I forgot the integral constant here. I'm sorry. I integrate this from this one to this one. There must be integral constant here, which is this, which is independent of x. It may depend on t. In the case of periodic boundary condition, we have this equation. Okay, periodic boundary condition means this one. Therefore, this is a nonlinear heat equation, but its evolution comes with a constraint of this. So every time constraint is maintained, so integral is always 0. Therefore, we must subtract L2 norm of U, capital U. Then, in other words, we should consider the nonlinear heat equation in this function space, which is L2 divided by R. R means constant function. Therefore, this is orthogonal projection. It was not easy for me to prove that the solution blows up in this case. But finally, I succeeded. Therefore, this one blows up. So this one, there is no blow up. This one, blow up exists. Therefore, this one was very important, I realized. This one is not appendix.
But the stretching term, if you remove the advection term, arguing from where it came from in the momentum equation, you would have to remove the stretch.
No, I will come back to that issue very soon.
Is it because the question is whether it's fair to do this?
A proper convection term prevents solutions from blowing up. Okay? I skipped this one. Now, then my motive to introduce this equation with A, general A, is that so convection term is important to prevent blow up. And if stretching term is big enough, then blow up exists. Therefore, if A is large, blow up. If A is small, like if A is 0, no blow up occurs. So that folklore, which I introduced in the beginning of my talk, is that can we determine for which A blow up occurs and for which A its blow up does not occur? So by this way, I wanted to mathematical formulation. I want to have a mathematical formulation for that folklore. And that one is here. And the question is, how large it must be? It means A. A must be. A question. This one was again proof depends on his argument. Xinfu Chen. I think he's still working in Pittsburgh, University of Pittsburgh. Yeah. The theorem is that if nu is the positive and A is between -3 and 1, then the solution exists globally in time for any initial data, small or large. So this is a mathematical statement. Now, this is a current status, which I want to invite you for the proof. Now, this equation with parameter A runs from -infinity to +infinity. And this is nu positive, this is nu 0. Green means we have a proof that the solution exists globally in time. So if A is not so large, there is no singularity. But if A is big, my computation suggests they just blow up. But this question mark means I don't have mathematical proof. I have many numerical computations. Computational result suggests the blow up occurs in this and this and this, but I can't prove. This one, there is a proof. This one, too. So this is one motivation which I introduced, the new parameter A. But a numerical experiment can be very deceptive, I would say. In this case, where stretching term is 0, stretching term is 0. Therefore, in that case, there is no singularity. I can prove. Okay. For this strange equation, we have a mathematical proof that all the solutions exist globally in time. But the numerical computation looks like this. T is here from 0 to increase in this way. In this way. It goes this way. Therefore, this is the profile of the solution. So it means this very steep part becomes steeper and steeper. So eventually, numerical solutions fail to compute eventually. But there is a mathematical proof that the solution exists globally and solution is C infinity. There is a proof. But numerical computation stops around here. Therefore, numerical computation itself is not enough for this kind of problem. If A is -3, smaller than -3, or A is bigger than 1, then there is something like this. If A is 1.1, solution looks at this and it blows up. If A is 1.05 with the same initial data, it goes in this way. If A is 1.02, it's very slow, but eventually it goes in this way. But if A is just below 1, it becomes very large and goes to 0 eventually. So A is 1. The Proudman-Johnson equation's case is a border point. I want to show pictures of the numerical solutions. Okay. Sorry. Only Chinese and Japanese can read this one. Okay. This is the case when A is very large. A is 10. This one becomes bigger and bigger. Convection term exists, but stretching term is much bigger. So eventually it grows up. So let me show the solution once again. At the beginning, the movement is very slow. But once it becomes this one, then goes to infinity very quickly. This one is the same picture, the same solution, but different scaling. So every time I divide the solution by the maximum norm. Therefore, maximum norm is always 1. With this normalization, this is the point at which omega takes maximum, and then what happens? So only this one becomes infinity, or this one becomes goes minus infinity, but relatively much smaller than this one. Either way, I don't know which happens in this particular equation, but so numerical experiments suggest that this is the case. I mean, this goes to infinity, but so I suspect that this one goes to plus infinity, other place goes to minus infinity. But minus infinity is much weaker than the plus infinity. But again, I don't have proof. This one, this one. Oh, I'm sorry. Quite a different boundary condition. It's not a periodic boundary condition. We fix some Dirichlet boundary condition. In that case, blow up occurs here, and it goes to plus infinity eventually. So, there are many other similar problems and similar propositions for each differential equation. And so far, my numerical experiment suggests that this folklore is correct in some sense. In some sense, I say. Because I don't have much time, I want to skip this part. There are many conjectures, but conjecture is a conjecture. I need some proof. I want to skip this too. But there's another interesting equation. So far, I consider two-dimensional flow. So vector field is 2 dimensions. But I can consider the similar idea in a 3-dimensional vector field. In that case, ansatz is something like this. This ansatz was used by C.C. Dean in 1957, and Grundy and McLaughlin in 1999, and my former student too. And then we have a couple of equations. F and G are both unknown functions. If G is 0, identically 0, then this becomes a Proudman-Johnson equation. In this sense, this coupled equation is a generalization of Proudman-Johnson equation. Now, for this equation, we have a conjecture that the solution blows up. So in 2 dimensions, Proudman-Johnson, there is no blow up, which we proved. But in 3-dimensional model, this one goes to infinity in a very short time. And probably, I believe, the solution blows up in finite time in this coupled equation. But again, I don't have time, proof. Another one is the constant in Lax-Meyer. But this one is this equation involving Hilbert's transform. This Hilbert transform causes a lot of trouble. But I can consider this kind of generalization, I'm sorry, this one. And then this one combines all the solutions, Proudman-Johnson equation, constant in Lax-Meyer equation, and even some water wave equation if nu is 0. Therefore, this kind of generalization is not a general nonsense. It combines Berger's equation, constant in Lax-Meyer equation, Proudman-Johnson equation, and some, not many, but some water wave equation. Well, I don't have time to explain, but I think I should stop here. Conclusion is here. As I said before, a proper convection term prevents the solution from blowing up, or at least rapid growth is slowed down by a convection term. There are some cases where proof is needed, because many of my conclusions are based on the numerical experiments. Blow-up behavior is very different from a nonlinear heat equation, because my model is a non-local nonlinear equation, and that is very different. And more problems can be found in the paper and this paper. Thank you very much for your attention.
In your opening salvo, you've introduced the function u from the German paper. What does that u represent physically?
It's a kind of stream function.
It's not quite a string function, is it?
No, 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 of course not. Oh. But this ansatz is not actually Himen's ansatz. Himen himself said this ansatz comes from my mentor, which is Prantl. So Ludwig Prantl came up with that thing. So I don't know how he found it, and there's no explanation from me. I'm sorry.
Sometimes geologists use functions of that form,
Uh-huh.
but they don't worry about far fields or
Of course, yeah, yeah.
when they're looking at folding in rocks on a slope scale. That's the sort of function that they look at.
Mhm. Yeah, in that case, in that particular case of Himen, there's a stagnation point on the wall. So his analysis applies near the stagnation point. For that matter, it's totally okay. Yeah, but for far field, of course not.
I was wondering, how is this kind of folklore, how is it consistent, for example, with the SQG, if you think? For the SQG equation, you also have a convection term. You have no stretching, but still it's not known if there are global solutions. So how is this consistent with other equations?
Now, if you differentiate SQG, for instance, then you have a different picture. Okay?
Yeah.
So Berger's equation has no stretching term in U form. But if you differentiate Berger's equation in X, then both nonlinearity, convection and stretching, both appears. And which one is more important? Both are important. That is my conclusion. Yeah. So if necessary, we must differentiate or integrate in X. Then under that condition, that folklore is correct, I think.
Also, convection, in my mind, sometimes to do with incompressible. If you have like a vector field that, because at the beginning you said that the convection term just rearranges.
That's right. Yeah.
It won't happen if it's not incompressible.
For incompressible, I have not considered. Yeah. No. Yeah, I consider only incompressible fluid form.
Okay, questions? Let's thank the speaker.